CERN is a European organization with a lot of experience in detector construction, in assembly of detectors, so we were helping there, the AMS collaboration. There's a special clean room at CERN within which the experiment was built together. Secondly, you have to calibrate such a detector, such an experiment, before you send it to space. So we used the CERN test beam facilities in order to calibrate that detector. And thirdly, and that's very nice, for the next years, we are in the Science Operations Center here at CERN for AMS. That means we will have a direct link to the International Space Station, and we'll get the data here, and people will be here to analyze these data. So that's very exciting. So first of all, it shows that independent if you have space-based or ground-based experiments, they can use and very often use similar or even the same technologies for the experiments, for the detectors. And they also address similar questions. For example, where is the antimatter in space? Why is there essentially no more antimatter in space? These are questions which AMS will address, because they are looking for antimatter in space. And the LHC will address the question, why the antimatter has more or less disappeared. So very complementary attempts to look at the similar question.
Plus we've done all of the that point is camera. Where's the camera? Okay. 2 hours before launch, so 2 days before launch, you unlock the program. So it's fell down by 4 bolts. Come up there right there. You see the shuttle itself, as I mean, you see the red flag, right?
The universe around us seems to be made up of much more than what we can see. Indeed, the visible mass appears to be only a small fraction of the estimated total mass in the universe, and the observed motion of this visible mass suggests that it is mere flotsam on an invisible sea of unknown material. Galaxies are observed to rotate much faster than the visible matter in them requires them to. It would seem that invisible matter is stopping them flying apart. One explanation being postulated is that we are wrong to assume that gravity is unchanging and consistent over vast distances. Perhaps our current theory of gravity needs modifying. Another explanation could be that associated with each galaxy is an invisible halo of so-called dark matter, and it's this that's responsible for the galaxy's fast rotation. Looking for this dark matter will be CERN's Large Hadron Collider in Geneva, which will be on the hunt for an entirely new type of particle. It's long been known that particles such as electrons have a mirror twin with opposite charge. These inhabit the strange world of antimatter, loved of science fiction writers. In this case, the antimatter partner of an electron is a positron. In the presence of an electric field, they move in opposite directions. But CERN will be looking for an even stranger pairing. At the beginning of our universe, a minute blob of time and space, far smaller than an atom, began to expand as a way of dissipating its extreme energy. Such three-dimensional spatial expansion that happens everywhere and all around us is well represented by this two-dimensional surface of a balloon that is stretching as it's been blown up. The Big Bang into pre-existing space is now seen as the big stretch of space itself. After a moment of extraordinarily fast expansion, the blob seems to have contained a plasma of particles. On further stretching, the quarks and gluons condensed into protons and antiprotons which almost annihilated each other. But not quite. The few protons left over formed the basis of the universe we now live in.
At this moment, the Big Bang, pure energy, is released. In a furnace of heat, space expands at incredible speed. In the tiniest fraction of a second, our universe is born. This is the deepest of all mysteries. Some of the energy now condenses into matter. At this moment, all the particles that make up our universe are created. Some we do not understand yet. Among the others are incredibly small quarks, electrons, neutrinos, particles that will make everything we know, including you. Look closely. They come into being as pairs, particles and their opposite antiparticles. Fatally attracted, they annihilate each other. But some of the matter survives. Fortunately for us, matter that makes up everything we know.
There's JSC or here that can make that.
Yeah. So be careful. Yeah. This is the high gain. You can see it's protected. So worst case, I mean.
This is sensor 2. This is sensor back.
You don't have any. You guys don't have any intensity.
It's like if it's raining over Geneva, and you have a one drop which is red, and you catch it without hesitation and understanding there is something strange going on. Similarly, we are going to catch billions and billions of cosmic rays looking for exotic components, very rare one. Antimatter is studied and produced in laboratories like CERN, in hospitals, for many, many applications routinely every day. So why we go to space? Very simple. We are looking not for the simplest antimatter, not for the simplest antiparticle, but the complex form of antimatter, like antinuclei of helium, carbon, oxygen. After the Big Bang, there was no oxygen, no carbon, no uranium. This has been built in the stars. So you see very immediately that the moment we see an anti-carbon or an anti-oxygen, there is immediate indication that somewhere in the universe there are large amounts of antimatter in the form of anti-star, building by fusion from lighter antimatter into heavier antimatter. AMS will be launched, and after 8 minutes will reach the space. The time to go to the atmosphere is only 8 minutes. Then will be switched on, but only for the purpose of controlling the temperature. For the following 3 days, we'll be orbiting around the Earth, getting closer and closer to the space station, and it will dock on the 4th day. There will be some activity by the astronaut by manipulating with this special crane and robotic arms, and then within a few hours will be installed in his final position. From that moment on, we're talking about the 4th day in space, we can switch on AMS, and within a bunch of minutes, half an hour or so, it will be on.
We're trying to see how our world has come about. Why are we here on Earth at this time? We probably come from a Big Bang where matter and antimatter have been produced together, and here we are, made of matter, and there's no antimatter. So this is a fundamental question that we would like to understand. A project like AMS allows to better understand what is fundamental research and explain to the general public what the scientists are doing. When scientists get together to try to solve some fundamental questions, and here we're talking about fundamental questions like the existence of dark matter or antimatter in space, then scientists can get together, even if they come from different countries, from different regions. They can really work together, and I'm very glad that also CERN was sensitive to that project and played a major role in allowing us to use their facilities.
Cosmic rays have been discovered about 100 years ago. It is particles that are produced by star explosion in its vast majority, then are somehow mysteriously accelerated and directed towards us. There's a lot of this radiation that comes on the Earth's surface. It's about several hundred per square meter per second. So it's not a small effect. It's a major ingredient to the environment of the Earth. It has something to do probably with genetic modifications. It has something to do with the climate. It has a lot of implications for us. And this means that we must absolutely know more about it than we do today. Dark matter is a very mysterious phenomenon. We know it is there because we see the gravitational action of dark matter all around the galaxies. Practically every galaxy that we know about has a halo of dark matter around it that does not emit light. So it's not visible by telescopes, but it is visible by the motion of objects around the galaxy. Now we have no idea what it consists of just because it doesn't emit light. So the traditional way of observing cosmic phenomena is just not working for this kind of matter. So what AMS will be looking at is secondary effects that have to do with maybe self-annihilation of dark matter particles with themselves. When they collide, they may produce a charged particle. They may produce antiparticles also, and that is what we are after. For all we know, in the beginning of the universe, at the Big Bang, matter and antimatter have been equally created. Now, for some mysterious reasons, antimatter seems to have disappeared because the Earth, the solar system, our galaxy, even the cluster of galaxies that we live in is for the vast majority made of matter, not antimatter. So somehow half of the universe has mysteriously disappeared. We would like to know whether there's any left at all. There may be none left, and we will know that after the end of this experiment. We will know if or not there are small amounts of antimatter left.